In 1869, on the basis of physical and chemical properties, Mendeleev gave law of periodic table, which is known as the physical and chemical properties of elements are periodic functions. This is just the keyword. In the definition, your teacher will be looking for two keywords here: periodic function and atomic weight. In Mendeleev's periodic law, in modern, he will be looking or she will be looking for periodic function and atomic weight, atomic number instead of atomic weight. Atomic number. That's now important contribution means what were the important characteristics of this particular table, Mendeleev's table. First of all, systematic study of elements was possible. So we didn't need to remember the properties of all the elements. We just needed to remember the properties of groups, specifically specific groups. Second, correction of atomic masses. A few atomic masses were not marked correctly. So based on the properties that yes, properties are matching, some atomic masses were adjusted. So for example, atomic mass of beryllium was corrected from 13.5 to 9. Initially, it was calculated 13.5, but it was then corrected to 9 according to its properties. Similarly, with the help of this table, atomic masses of indium, gold, platinum, etc. were corrected. Although these questions highly unlikely that will be asked, but just for reference, you should remember beryllium, indium, gold, and platinum atomic masses were corrected by Mendeleev's periodic table. Then prediction of new elements. Mendeleev was able to predict other elements because there was a gap of atomic masses, a large gap. So he said that new elements will be discovered and atomic mass will lie in between these known ones. So only 56 elements were known at that time. Currently, we have 118. While arranging these elements, he left some gaps. These gaps represented the undiscovered elements. So prediction of new elements was possible. So for example, he predicted the properties of gallium. He called it Eka aluminium, and germanium he called it Eka silicon, because germanium and silicon were known at aluminium and silicon were known at that time. So based on that, he said that gallium will be there. It will be below aluminium, and silicon will germanium will be there. It will be close to silicon. So Eka aluminium, Eka silicon. Sometimes this is asked, so you can just memorize.
Excuse me, sir.
Yes.
Sir, I have a question, but it's not actually very related to the topic.
It is basically not related to, and a previous in previous year it was actually deleted, but in
No,
many
sir, I
schools it
have
is
a question that I want to ask, but it's not very
okay.
much related to this.
Okay,
So
fine.
should I ask
Ask.
it now or later? Sir, if these elements were not discovered, then how could you understand what properties will they have when they will be discovered?
No, he didn't say what properties. Basically, if you see the properties are, for example, changing. Say the atomic mass is 11, then 13, then 15, then 17. It is like that. It is in this fashion. So that is why what we are talking about periodic repetition. Okay, periodic means after certain, it repeats itself. After certain elements,
Period.
it will repeat. Okay? And similarly here, for example, then it got repeated like say 25, 27, 29, 31. Out of 56 known ones, when he placed them, suppose it is like this. So he said because it is 11 to 13 here, and it is 29 to 31 here, but this much gap will not be possible. So it means there should be one element which will have properties similar to this one, because this element had properties similar to this one, this element
Okay.
had properties so similar to this one. So it means there will be some element we will discover in future which will have properties too similar to this one, another element properties similar to this one.
So, sir, he just basically predicted that element.
He predicted these two elements, he predicted, which were actually named as gallium and germanium when they were discovered. He called these as Eka aluminium and Eka silicon because these were close to aluminium and silicon properties. respectively. So he could predict based on the missing numbers. So if I'm writing, say, 1, 2, 3, 4, 5, 6, 7, 8, and this one, there is no element having this particular atomic mass. So he said there should be something here which is not known. Then defects of Mendeleev's periodic table. Having said that, there is a possibility that this year also this particular part, that is Mendeleev's periodic table, is not in your syllabus, might be, but no confirmation from CBSE side till now. Defects of Mendeleev's periodic table. Position of hydrogen. Position of hydrogen was at all not discussed in Mendeleev's periodic table. Okay, so hydrogen is placed in group 1 arbitrarily. However, it resembles the elements of group 1 alkali metals as well as the elements of group 7A. It was called as 7A at that time, which is now group 70. So in Mendeleev's periodic table, it is group 7A. Only 56 elements were known at that time. So obviously we had less number of groups at that time. So we were not able to, he was not able to place hydrogen in any particular group. He said it should, yeah, I'm placing it in group 1, but no reason behind that. Then anomalous pairs also. In certain pairs of elements, the increasing order of atomic masses was not obeyed. He said that, okay, atomic masses are not in increasing order, but I am placing them as per their properties. So he overruled his law itself. So in these cases, Mendeleev placed elements according to similarities in their properties and not in increasing order of their atomic masses. So a few elements were there which were not placed according to the law itself. For example, argon atomic mass is 39.9 was placed before potassium. So if atomic mass is 39.9, it should come after potassium, but he placed it before potassium. Why? Because argon had properties similar to noble gases. That's why he placed with noble gases. Similarly, cobalt, atomic mass 58.9, placed before nickel. Nickel atomic mass is 58.6. But he was not able to explain why. He just said because properties match, that's why these need to be placed with each other. Tellurium, atomic mass 127.6 was placed before iodine, atomic mass 126.9. You need to remember atomic mass of iodine 127 normally, okay? Instead of 126.9, use this one. It will be required in many calculations, so you should remember atomic mass of iodine 127. These positions were not justified. So what we are talking about, defects of Mendeleev's periodic table, why we needed modern law. So the first one was here position of hydrogen was not defined. Second, anomalous pairs, means these pairs were not in correct order of their atomic masses. Position of isotopes. We know that we have isotopes, for example, carbon isotopes 6C12, 6C14. So there are two atomic masses, 12 and 14. Where to place? Because this law said we need to place elements according to their increasing atomic mass. So if we say 6C12 and 6C14, which one we should consider? And where we need to place these two differently if we want to. So isotopes are the atoms of same elements having different atomic masses but same atomic number. Therefore, according to Mendeleev's classification, these should be placed in different places depending upon their atomic masses. But they were placed at the same cell, in the same cell. So for example, isotopes of hydrogen with atomic mass 1, 2, 3 should be placed in 3 places. However, isotopes have not been given separate places in periodic table. They were placed in just one cell. So this was another defect. Some similar elements are separated and dissimilar elements are grouped together. Although Mendeleev said that depending on the property, I will place argon with noble gases and I will place it before potassium, even if argon's atomic mass is greater than potassium. So there he said, I will match the properties. But in certain cases, similar elements were separated. They were not listed together, but dissimilar elements were grouped together. So for example, copper and mercury resembled in their properties, but they had been placed in different groups. They were not in same group. Different groups, even when they resembled the properties. At the same time, elements of group 1A, lithium, sodium, this is Na, and potassium were grouped with copper, silver, gold, etc. Though their properties are quite different. So in the table, he was not able to explain what is the reason he is placing these together in the same group, okay, when properties are not same. So he was not able to explain. He just arranged in increasing order of atomic mass, and when he placed in increasing order of atomic mass, these were grouped together, even though when their properties were not same. In Mendeleev's table, current group 1 was group 1A. Cause of periodicity, he was not able to tell that. What is the reason? Okay, you are saying that we, if I'm placing it in increasing order of atomic mass, but what is the underlying reason? He was not able to explain. However, in modern periodic law, we were able to explain on the basis of number of electrons in valence shell. Atomic number means how many electrons will be there, how many protons will be there, how many electrons will be there, and on that basis, how many valence electrons will be there. So this was not possible in case of Mendeleev's table. Position of lanthanoid and actinoids. So this is something you should already know from your previous grade. What are lanthanoids and actinoids? Just let me know if you don't know.
So please tell.
Okay.
Yes.
Lanthanoids and actinoids are the elements, 14 elements. Lanthanoids, these are 14 elements. Actinoids are 14 elements in current periodic table. Okay. These elements are those ones which have very similar properties. Lanthanoids have properties similar to sixth period, third period. And actinoids have properties similar to seventh period, third. Group is same, third. I'll show you that just in a few minutes. This is first, second, third group, and first, second, third, fourth, fifth, sixth, seventh period. Okay. So I'm talking about these cells. This one, and this one. Sixth period, third group, seventh period, third group. So all lanthanoids are placed in this cell only. All 14 actinoids elements are placed in modern periodic table here, seventh period, third group. And the reason is they have very similar properties as to lanthanum and actinium. Lanthanum and actinium are original elements which are there in sixth period, third group, and seventh period, third group. Okay, these are original lanthanum and actinium. But because these 14 elements after lanthanum have very similar properties, they have been placed together. So altogether there are 15 elements. Lanthanum plus these 15 elements in one cell. These all are known as lanthanoids because these are with lanthanum. These all 14 are known as actinoids because these are placed with actinium. These have properties similar to actinium. So these are known as lanthanoid, actinoid. In case of Mendeleev's periodic table, it was not able to explain anything about it. Okay, the 14 elements following lanthanum, known as lanthanoids, from atomic number 58 to 71. So if you just see, these are 14. And the 14 elements following actinium, known as actinoids, from atomic number 90 to 103, have not been given separate places in Mendeleev's table. These have very, very similar properties. all lanthanoids and all actinoids. So that's why in current periodic table, these are placed in one cell, and these are actually F block elements. These are F block elements, 14, 14 F block elements. And if you remember from your previous chapter, and who will tell me, if I have F subshell, in F subshell, how many orbitals will be there? Who is going to tell me? You know the formula.
Sir, 7.
Okay, good. So Pratham, good. There will be 7 orbitals. Orbitals will be 7. 1, 2, 3, 4, 5, 6, 7. And in these 7 orbitals, total how many electrons can be there?
Sir, 14.
Sir,
14.
Yes, sir,
These
14.
14, each electron
14.
corresponds to 14 elements. Each electron corresponds to a different element. So for example, there is only one electron. Say there is only one electron in F subshell. So this will look like this. This will correspond to one element. Okay. Suppose there is another electron. So this will come in next orbital. This will correspond to another element. Similarly, another element, different element. So total 14 elements can be defined or depicted by F subshell. F block elements, 14 elements, these all have very similar properties, have been placed in which cells? 6th period, 3rd group, 7th period, 3rd group. All F block elements are there. I will be showing you the diagram. So lanthanoids and actinoids are nothing else the F block elements. In order to cover more elements, Mendeleev modified his periodic table. Now the modern periodic law. The only difference is atomic number. Periodic function is same. 2 keywords your teacher will be looking for. Periodic functions of their atomic number. Okay. Now this is the periodic table, how it looks like. And in this periodic table, the first 2 groups, these 2. Remember, I have included hydrogen here. Okay,
Yes,
are S block elements. First 2 groups are S block elements. Why these are S block elements? Because we have studied the electronic configuration. Suppose I talk about, say, lithium, sodium, potassium, 3, 11, 19. Lithium, sodium, potassium, and I write electronic configuration 1s2, 2s1. 2s2 will not be there because there are only 3 electrons.
yes, sir, 2s1.
Okay. 1s2, 2s2, 2p6, 3s1, 11 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now, what is the similarity? Similarity is that the valence electron is in S subshell, always. And that defines the block. If the valence electron is in S orbital, it will be S block. If it is in P, P block, D, D block, F, F block. That's it. So you write the configuration, valence electron subshell will decide the block. Similarly, if you consider, say, magnesium 12 or calcium 20, magnesium 12, calcium 20, you write the configuration 1s2, 2s2, 2p6, 3s2. Calcium 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Here again the electron, valence electron is in S subshell. So that's why S block. The number of electron, increasing order of number of electron will decide which particular group I am talking about. If it is S1, it will be first group. If it is S2, it will be second group. That's it. So here the configuration, if I say valence electron configuration of all electrons will be S1. Here valence electron configuration will be S2. That's how you will decide these are S block elements. Next one is P block. These are P block elements. Same condition here with respect to the electronic configuration. Same thing. Here it will be P1, P2, P3, P4, P5, P6. You know maximum number of electrons in P subshell 6. So from 1 to 6, each electron will decide the group. So 13 group will have P1, 14 P2, P3, P4, P5, P6 configuration. For example, if you write configuration of aluminium, silicon, phosphorus, etc. Aluminium 13, 1s2, 2s2, 2p6. 1s2, 2s2, 2p6, 3s2, 3p1. The valence electron is in P, and this is the first one. So this will be 13th group. It will start from 13. Similarly, say you write for phosphorus 15, 1s2, 2s2, 2p6, 3s2, 3p3. It is in P, it is P block element, and this is 13, 1 is 13. After that 14, 2, 14, and 3 will be 3p2 will be 14, 3p4 will be 16, p5 will be 17, 3p6 will be 18th group, noble gas. So noble gas configuration will always be 3p6. Valence electron configuration. Any confusion till here? Let me know. Good. Now next one is D block elements. These are all D block elements in between. That is group 3 to group 12. And now who will tell me that group 3 to group 12, these are total 10 groups. Tell me why these are 10 groups.
Because in the d orbital there are only 10 electrons.
Yes, yes, good. Amir, yes. Okay. So it's fine, correct. Because in D subshell there will be maximum 10 electrons. And 10 electrons from 1 to 10, each will represent 10 different groups. So it will be similar to that one, what we discussed in case of SNP. The group 3 electronic configuration, valence electron configuration will be D1, then D2, D3, D4, up to D10. However, there will be certain exceptions. Okay, exceptions will be there because in few cases, electron will move from lower energy state to higher energy state. For example, S to D to attain stability. For example, in case of chromium and copper. We have talked about these are anomalous. So instead of D4, chromium will have D5. Instead of D9, copper will have D10 configuration. You know why? You remember why?
Yes, sir.
Okay. In case of copper, the original electronic configuration was 4s2, 3d9. That is the configuration of that particular group. Okay, S2d9. But to attain stability, one electron moved from S to D. It became 4s1, 3d10. Now both are half filled and fully filled. This is half filled. So these are stable. So although I am saying that general electronic configuration will be as I am saying, There might be exceptions you need to take care of. And F block, I have already told you, these are the F block elements, all 14 elements lanthanoids and 14 elements actinoids. All the lanthanoid are here actually. These have been written separately, but all these are here. All these ones, actinoids, are actually here because they have properties similar to those elements. That's why lanthanoids and actinoids. But based on their electronic configuration, the valence electron is in F block. That's why these are called F block elements. Another point which you should remember, and many students have made mistakes earlier, lanthanum and these 14 are in same cell, 6 period, third group. But lanthanum is a D block element. It is not F block element. These 14 elements which are there in lanthanum, these 14 are F block elements, only these 14. These are kept with lanthanum. It does not mean that lanthanum is F block element. Lanthanum is D block element with configuration D1. First group of D block. Similarly, actinium is D block element. It is not F block element. The other 14 which are placed with it, these are F block elements and are called actinoids. Actinium is not actinoid. Actinium itself is actinium. These all 14 will be known as actinoids. Now, next topic is nomenclature with atomic number more than 100. These are guidelines given by IUPAC body, and the reason is earlier scientists used to find new element, and suppose two countries found or discovered the element and they named it according to their scientist's name. So to avoid that, IUPAC body said that no, we will be following some standards, and if any new substance, any new element is discovered, that will be named as per following conventions. Now, why only more than 100? Because up to 100, every element is named already. So we don't need names for the elements below 100 atomic number. 118 till now have been named. If any new appears, discovered, it will be named as per this logic. So for that, you need to remember this table. The digit 0 will be used, okay, and its name is nil. It will be pronounced as nil, and abbreviation for it will be N. So why I am talking about digits? I am talking about digits because the atomic number will be in digits. For example, a new substance is found as 119, 118 known. Next one will be 119. So I need to name it on the basis of these digits, 1, 1, and 9. Okay. For these, there are certain defined conventions that 0 is called a nil and abbreviation is N. Why we need nil and N both? Because every element has a name and abbreviation. For example, aluminium is the name, Al is abbreviation. So I need a name of that particular element. I need the symbol also. So for symbol, I will use abbreviation. One will be known as and abbreviation will be U. You need to remember all these. Very simple question appears from here. So in your first UT, certainly there will be one question from here. Questions actually start from this topic. So you will be asked that atomic number 132 element is discovered. What will be its name? For that, you need to use the name that it is 1. For 1, you will use UN. You will write UN. Then it is 3. So for 3, it is tri. You will write TRI. Then there is 2. So for 2, you will write pi. And ending will always be in ium. Ending will always be in I'm just showing you. For example, 101 is named as 1 is un, 0 is nil, then 1 is again un, and ending will always be em. That's what you will do. In this case also, you will here write em. Okay, that's how it will be named. Remember, you don't need to write I 2 times. That's why if you see here, I have written only 1 time. Although 2 will be by and I need to end it with em, it does not mean that I will write I 2 times. Here I will write only uf. So I would suggest that you memorize these values. These are very straightforward. Nil, un, bi, tri, quad, pent, hex, sept, oct, n. For 9, you might not be knowing already. Otherwise, all are you can remember by common sense. These. So this is up to the time IUPAC body does not decide the actual name. So when they will be discovered, this name will be given. After that, IUPAC body will decide that what will be its actual name. Okay. So that's why if you see 104, the name as per IUPAC convention was un nil quadrium. So for 1 symbol was U, for 0 symbol was N, for 4 symbol was Q. So this was the symbol. After that, it was given the name Rutherfordium R. So this will be the convention that if any new element is found, discovered, first it will be given the name like this so that the countries do not give their names, and then IUPAC body will decide the actual name. These are the 4 blocks I discussed: S block, P block, D block, F block. S and P block together, S and P block together are known as representative elements also. Together, sometimes if you come across in question, what are representative elements? S block and P blocks together are called representative elements. D block elements are called transition elements. Transition elements. And the reason is that these are in between S and P block. So when you move from S to P, after S, it is P. But when you move from S to P, it is not direct. You transition through D block. So that's why the name given transition elements. However, there are other points also to support why these are called transition elements based on the movement of electron, which I will be talking about later. But this is common answer. If you are asked why these are called transition elements, because these sit between S and P block, and to move from S to P, we have to transition through the D block elements. Now S block elements. So one by one, quickly we will talk about these elements. Elements of group 1. Group 1 elements are called alkali metals, and group 2 elements alkaline earth metals, which have configuration valence electron configuration as ns1 and ns2, belong to S block elements. You know group 1 and group 2, alkali metals and alkaline earth metals. What is an alkali? Tell me. What do you understand?
Bases that dissolve in water.
That dissolve in water.
Okay.
Basic elements which are soluble in water.
Yes. So they are the bases which are soluble in water and can form solution with water are alkali. Good. Then alkaline earth metals means their compounds are found in Earth's crust. They are also alkaline in nature, but these are found in the earth crust. That's why alkaline earth metals. They are all reactive metals with low ionization enthalpy. All group 1, group 2 elements are basically very reactive. So if I talk about lithium, sodium, potassium, rubidium, cesium, francium. These are very, very reactive metals, and francium is actually radioactive. Okay. So normally we will talk about the chemistry of these five. Okay. Similarly, when we have the group 2 elements, okay, so we have
So what is meant by ionization enthalpies?
okay, I'll tell you just a few seconds. So group 2 elements, boron, magnesium, calcium, strontium, barium, and radium. These are again very, very reactive metals. All group 1, group 2 elements are very reactive. All these are metals, very reactive metals. Hence, these are not found in pure form in nature. They are always found in their compounds, in the form of compounds. So if the question appears that why these are not found in the form of metals, these are metals, but not found in that form. The reason is they are very much reactive. They have very low ionization enthalpy. That's why these react with other elements and are found in the form of compounds. Now, low ionization enthalpy means the ionization is very easy. So, for example, Na to Na plus. How ionization takes place? So, Na to Na plus means it has lost one electron. It has lost one electron. So that's why it got converted to sodium ion. And this is caused ionization. In case of these metals, ionization enthalpy is very low. Means if I am talking about sodium, this is nucleus, first, second, third shell. Here you will have 2 electrons. Here you will have 8 electrons and 1 electron in third shell. This electron, valence electron, can be removed very easily.
So the amount of energy required to remove an electron is less.
Yes. It can
Okay.
be removed very easily means it requires very low amount of energy. It means ionization enthalpy is very low.
Okay.
They lose the outermost electrons readily from +1 ion in the case of alkali metals and 2 plus ion in case of alkaline earth metals. Means if I am talking about alkali, we will get Na plus. And if I am talking about alkaline earth metals, for example, magnesium, I will get Mg2 plus and it will lose 2 electrons. The energy required in these cases is very low. Because of high reactivity, they are never found pure in nature. The compounds of the S block elements, with the exception of those lithium and beryllium, are predominantly ionic. And that's why these are important, because in chemistry, you will get many questions from exceptions. So if something is different from regular behavior, you will get questions from there. Lithium and beryllium have higher covalent character. More about it, we will be talking about in chemical bonding. But for now, you need to understand that all other elements except lithium and beryllium, lithium in group 1, beryllium in group 2, all other elements are predominantly ionic. Now, whenever we say ionic and covalent, no compound is 100% ionic or 100% covalent. It is about which character is higher. So normally, ionic character will be higher. Say ionic character is 90% or 95%. For in case of NaCl, for example, sodium chloride, ionic character is very high, more than 99%. So that is actually predominantly ionic, less than 1% covalent character. But compounds of lithium and beryllium will have covalent character higher. So that's why These are different from other elements of the S block elements. P block elements. P block elements group 13 to group 18. We have seen P1 to P6 outer electronic configuration. The S block and P block elements together are called representative elements or sometimes main group elements. Hardly you will get written as main group elements, but representative elements you might get written in your exam. You need to remember. The outermost electronic configuration varies from NS2 and P1, NS2 and P6 in each period. At the end of each period, we have noble gas, and that will have the configuration fully fit. S block, S shell, subshell completely filled, P subshell completely filled. All the orbitals in the valence shell of noble gases are completely filled by the element. And it is very difficult to alter this stable arrangement by the addition or removal of electrons. It requires a very high amount of energy to either get one electron into the atom or get one electron out of the atom. What is the reason? We will be talking about later. The noble gases thus exhibit very low chemical reactivity. The reason is very simple, because the electron gain enthalpy and the ionization enthalpy, electron gain enthalpy is positive and ionization enthalpy is very high. What are those energies? You will understand in next class. Now, preceding the noble gas family are two chemically important groups of non-metals. So you remember I talked about periodic table when, and these are the P block elements. 13, 14, 15, 16, 17, 18. 18 noble gas. These two are very important. Here we have 17 group, which is group of halogens. So they are halogens.
Chlorine, chlorine, bromine, iodine.
Yes, correct. And chalcogens, group 16. Sometimes you will be asked which group or which elements are known as chalcogens, which groups are known as halogens. You need to remember group 16 are given name as chalcogen, group 17 halogen. Nothing more than that. These two groups of elements have highly negative electron gain enthalpies. Now, when I say negative electron gain enthalpy, who will tell me what it means? The sign of energy is negative. What it means?
So meaning they gain electrons easily.
Fine, but what the negative means?
A negative no means energy is lost, sir, in terms of delta E, if we say.
Right. Negative means energy will be lost. If it gains an electron, now go word by word. It is written negative electron gain enthalpy. Highly, yes, it is high, that's fine. But the keywords are negative, electron gain, and enthalpy. Means energy. Negative means is released when atom gains an electron. That's what it means. And if you can understand this point here, it will be very easy for you to understand these type of questions later on. There will be confusing questions based on negative electron gain enthalpy later on. And those I am saying confusing because if you don't understand this concept, then otherwise straightforward. Negative means energy will be released when electron is, released when atom gains an electron. Electron gain means electron is gained. And readily add 1 or 2 electrons respectively to attain the stable state gas configuration. This point I will slightly explain in details. It is very important point and many important questions appear from here. You have outermost electronic configuration, say I am talking about of group 17. So let's talk about group 17 element chlorine. Chlorine has atomic number 17. So its electronic configuration, I am saying broad electronic configuration will be 287. Means on in first shell 2 electrons, in second shell 8 electrons, in third shell 7 electrons. So if I'm talking about this is the outermost shell, there will be 7 electrons in case of chlorine. 7 electrons. I have drawn only the valence shell. Now, if it gains 1 electron, when it gains 1 electron, its electronic configuration, valence electronic configuration I'm talking about, will be 1, 2, 3, 4, 5, 6, 7, and the other electron which it has gained, this one. Now, what is special about this configuration? What is special about this configuration? What it has attained on the right hand side? Who will tell me? In this case, this configuration is of noble gas configuration because the outermost shell is completely filled. The electronic configuration of chlorine was 1s2, 2s2, 2p6, 3s2, 3p5.
So, sir, its outermost electronic configuration becomes NS2 NP6.
Yes. Cl minus means it has gained 1 electron. Now, instead of 17, there are 18 electrons. So configuration will be 1s2, 2s2, 2p6, 3s2, 3p6. Now the valence shell is completely filled. It means it is noble gas configuration. And it is very stable. Noble gas configuration is most stable configuration in periodic table. So if it is a stable configuration, and if you remember, I told you something related to energy. If anything is very stable, its energy will be low or high.
Sir, energy is low.
Okay, that's good. And I gave you example also. If you remember, I said that if you have water, cold water, it will be stable. But
Yes, sir,
if
with
you
boiling
start
water, sir.
boiling it, boiling water is not stable. So means if energy is low, it will be stable. If energy is high, it is unstable. That is something you have to remember, the analogy. It will help you. So here in this case, if it is very stable configuration, it means its energy will decrease. Its energy is low. Here energy was higher. Here energy is low. A stable state configuration will have lower energy. Unstable configuration will have higher energy. So if it has moved from higher energy to lower energy, it means rest of the energy is released. It will go into the environment. Is that clear or not? The energy was, say here 10 units, 9 units, say, and here energy is 5 units lower. So rest 4 will go into the atmosphere, will be released. It means it lost 4 units of energy. Because it lost that, that's why the sign negative. When it gained the electron, it achieved noble gas configuration. Because noble gas configuration is very stable, the energy of the product, what is formed, is low. That's why rest of the energy will be released. That's why negative sign. And when it is happening when it gains an electron. Is the concept clear or not? Why it is negative
Yes,
electron
sir.
in enthalpy? Okay,
Yes, sir.
because it is attaining a stable state configuration. Now come to highly. Highly means the amount is very high. The released energy is very high. Higher the energy released, more stable the configuration will be, because if energy released is say 8 units, higher energy, so I will say -8. So the remaining energy will be only 1 unit. So highly negative electron gain enthalpy means very highly stable product. So in this case, if you are asked that why in case of halogens, they have very high negative electron gain enthalpy, these are the steps you will write. What you will say? You will say the electron gain enthalpy in case of halogens is very high because first, when halogens gain an electron, they achieve noble gas configuration. Which is very stable configuration. Hence, energy is released and it is negative. When energy is released, it is negative. That's what you will explain. Next is D
So,
block.
sir, how exactly would we define electron gain enthalpy?
Electron gain enthalpy is the energy released when an atom accepts an electron, gains an electron. That is the statement I had written earlier.
Okay, sir. And because the energy is released, it is negative in these cases.
Yes, yes.
Okay, sir.
D block elements, transition elements. Remember, all D block elements are not transition elements. I am writing it. Although we normally say D block elements are called transition elements, but all D block elements are not transition elements. And there is reason. Okay? The reason is what I said, that there are other definitions also which we use to explain the transition definition. These are from group 3 to 12. You know that these are characterized by filling the inner d orbitals by electrons. Now, why we say inner d orbitals? The reason is, and question might appear from here as well. If we talk about the Aufbau principle, the filling up of electrons is like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. So if you see, we are going forward 3s to 3p, and from 3p we go to 4s, means higher shell, and from higher shell we went back to the inner shell. 4s shell is this one, so 3 shell, this is fourth shell, this is third shell, third shell is inner shell. So from fourth we are going back into inner shell, inner orbit. That's why the term inner d orbitals. Okay, so these are characterized by filling of inner d orbitals by electrons and are therefore referred to as d block element. Why? Because the valence electron goes into d subshell. Inner keyword why I have used, I have explained. If there is any confusion, you can ask. This is general electronic configuration of d block elements, and very important thing. You will directly be asked about this configuration. Write down and memorize. Many students think that they will be able to write it and then get confused in the examination. I will tell you why. Because normally, if you write as per above principle, and I said it is 3s2, 3p6, 4s2, 3d10. This is something I wrote. So normally students think that, okay, this is the outermost electronic configuration. I will write it as ns2 and n minus 1 d10, because this is what looks like. Here you have 2, here you have 10. So you say here it will be 2 always, and here this will be 1 to 10. You remember what I am talking about. You understand what I am talking about. P block elements generally will have 1 to 10 electrons, and that's why 10 groups there. So this will be correspond to third group, 10 will correspond to 12th group. It will start from third to 12th group in the periodic table. Okay. So if there is only one electron in D subshell, third group, two electrons, fourth group, and so on. So you will say in D, 1 to 10 electrons will be there. Those will decide the elements. But if you understand the exceptions, chromium, copper, etc., in that case, it is not always 2. It can be from 1 to 2, normally 1 to 2. But there are cases where these will be 0 to 2 also. That is something I will discuss in detail later on. So it is not always that it will always remain filled. No. So that's why the configuration will be either you write this one first, 4s2, and then 3d10 configuration. And if n is 4, then 3 will be n minus 1. So that's why I have written if n is 4, then 3 will be n minus 1. And I told you somewhere in previous classes that sometimes it is not written in terms of Aufbau principle, in terms of increasing energy. Rather, it is written in increasing order of shell. So n minus 1 is written first and then n. N minus 1 means previous shell to valence shell. So valence shell is fourth, previous shell is n minus 1, third. And this is the general electronic configuration you must remember. Write down and memorize. They are all metals. S block elements, all metals. P block elements, all metals. F block elements, all metals. It is only P block element, P blocks elements which have non-metals, metalloid, gases, etc. S, D, F, all metals. Okay. They mostly form colored ions, exhibit variable valence. Okay. Here it is written oxidation state. We will be talking about oxidation state in 8th chapter, redox. Paramagnetism and oftenly used as catalyst. Most of the catalysts used in chemistry are from D block elements. Okay. And there is reason. That reason in detail 12th grade we will be talking about. Next, however, zinc, cadmium, and mercury. These are exceptions. So you need to remember why. Which have the electronic configuration as n-1 d10 ns2 do not show most of the properties of transition elements. I'm not saying they are not D block elements. They are D block elements, but they do not show properties of transition elements. So that's why these are not called transition elements. So you might get question also, out of which the elements out of which are not the transition elements. And there is a reason
Excuse
for
me,
it.
sir.
Yes.
Sir, I'll have to leave the class right now because I have a important school meeting that I'm being called for. I just got a call from my teacher.
Okay, Shashwat, fine.
Yes, sir, I'll cover it up. I'll watch the video as soon as it. So I'll cover up the part I left. Okay, thank you, sir. Bye.
Fine. Okay, fine. In a way, transition metals form a bridge between S block and P block. So these form a bridge in between. and thus take their familiar name transition elements. But as I said, there are other reasons also why they are termed as transition elements. F block elements. Okay. F block elements are known as inner transition elements. Now, why these are called inner transition elements? That if you consider this diagram, what I had drawn, you have S here and P block here, and you transition through D. When you move from S to P, you transition through D. But F block is even within D block. Lanthanoids, actinoids. So lanthanoids, actinoids, F block elements are even inner to D block elements. So that's why we say inner transition element. F block elements are inner transition elements. Other reasons, as in case of transition elements, other reasons are also there for calling these transition elements. And similarly for F block elements, other reasons as inner transition elements, we will discuss later. So the two rows of elements at the bottom of the periodic table, lanthanoids and actinoids, are F block elements. It is important that you remember the range. Many a times there will be a question, and you need to remember this range because sometimes it will be asked that identify the element on the basis of the atomic number. And in next class, I will be talking about that, how you identify the element based on the atomic number, how you identify that in the periodic table. If you don't remember this range, you will make mistake. You will not be able to identify the element correctly. So 58 to 71 lanthanoids, 90 to 103 atomic number actinoids. You must remember this. General electronic configuration, again, very important. This is so important that you get questions on general electronic configuration in JEE and NEET as well. Don't take it lightly. N-2, F1 to 14, N-1, D0 to 1, NS. So for example, if I say N is 6, I am talking about the valence shell 6. So it will be 6s2, 5d0 to 1, and 4f1 to 4. If n is 6, n-1 will be 5, n-2 will be 4. The last electron goes in f orbital. That's why valence electron in f orbital, these are known as F block elements. These two series of elements are called the inner transition element, F block element. The one reason I have already told you. The another reason is, if you see as per above principle, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6p, 6f, 7s, 7p, like this. Okay? And if you see the filling up of electrons, you see when the electron is in 4s, sorry, 5s. After 5s, it goes to 4d, right? From here. But after 6s, I am talking about these two now. These two have 6th period and 7th period. In third group, have F block elements. After 6th, it goes to 4f. It means not just the inner shell. This was here inner shell. From 5s to 4d, it was inner shell. Okay. So it is just a transition. One transition. Only one transition from one shell to another shell. But from 6s to 4f, it is double transition. So it is say 6 shell, 5th shell, 4th shell. So first electron goes here in 6s, 6th period S subshell. Then it goes to 4f, means 4th shell F subshell. Means it comes back to inner to inner. So this transition from 5s to 4d is known as transition element. But if it is 6s to 4f, this is inner transition. One transition more within transition.
Sir, are the transition number of transitions solely based upon the shell number, sir? The value of n?
Value of n. Okay? So from 5th to 4th, this is transition. From 6th to 4th, it is inner transition. So that's why again the name inner transition. Second reason why it is called, these elements are called inner transition elements. Okay? For transition elements, there is one more reason which I will discuss in next class. Okay? So when we say inner transition element, this is the reason for F block elements, that the transition is from 6th shell to 4th shell, or from 7th shell to 5th shell. Here also 2 levels, 7 to 6, 6 to 5. In both cases, 2 transitions, that's why inner transition elements. These have been given them. So 2 reasons. First reason is that these are even within D block elements. So D block elements are transition, F block inner transition. That is one reason. Second reason, that when we talk about the above principle, filling up of the electron from 7s, after 7s, it goes to 5f. So it is inner to inner, that's why inner transition elements here. Any confusion, any point you need to discuss what we have discussed till now out of those points? Any point not clear, you can let me
So
know.
please show the previous slide once again.
Yes.